Welcome back to the second installment of our review series. We'll be talking about the periodic table in this one. And again, the idea of these videos is to hit on the main topics within each of the units, trying to keep it concise, based off of what the New York State Regents tries to test you on, test your knowledge on. So we'll start with filling in some of these blanks, and normally what will happen is I'll talk a little bit about them as we go. So the first thing that we talked about in this unit was groups are the names of the periodic columns. And it just so happens that elements that are in the same groups of the periodic table are going to have similar chemical properties. Now, this comes out to be because they have the same number of valence electrons. So examples, beryllium, which has 2 valence electrons, is very similar chemically to magnesium because there are also 2 valence electrons. Yes, magnesium is bigger. Yes, it has more electrons, but in that outer shell, in that valence shell of electrons, there are 2. And those are the electrons that determine chemical properties and chemical behaviors and bonding tendencies. So the valence electrons are very important, and it makes, the chemical properties similar within a group. We will find the most reactive metals are closest to the bottom of group 1. These are called the alkali metals also, additionally. Group 1 has the most reactive metals because they only have 1 valence electron. And achieving the empty valence shell is very easy for them to do. They only have to lose 1 electron. So they're very reactive because it's not very hard. In the example we were talking about before, yes, it's easy for these 2 metals to lose their electrons, but they have to lose 2. And it's not like they can just throw them out into the atmosphere. There has to be some reaction that takes them away. And group 1 only needs 1 reaction for its electron, but group 2 needs 2. And the further you move towards nonmetals, the less reactive the metals get, until you hit the staircase and you move on to the nonmetal side. Now, the most reactive nonmetals are not all the way to the right. They're at the top of group 17, not 18, group 17. These are called the halogens. Halogens are the most reactive nonmetals because, similarly but opposite, their valence electrons are at 7. So their goal would be to just gain 1. And because they only need to gain 1, and they're very good at gaining them, they tend to be very, very reactive. Some of you might be thinking, well, what about that last group? How can it be that they are not the most reactive group of nonmetals? Well, the group 18 people are very special. They're called the noble gases in group 18. They are very special because they are inert, and the word inert means unreactive. These elements, helium, neon, argon, krypton, xenon, radon, they're unreactive because they are filled with 8 or 2 valence electrons. Their shells are filled. Right? The outermost energy level is filled, which means 8. For the case of helium, it means 2 valence electrons. They don't react. a couple of terms that were very important for this unit were ionization energy and electronegativity. And most people get them confused. So the ionization energy is the energy to lose an electron. How much energy does it require to pull an electron away from the nucleus? That's ionization energy. Electronegativity is the opposite. It's how well an atom attracts new electrons. And what we do with these things is we kind of compare high to low, low to high, and we can determine which elements will lose electrons to the other elements that are going to gain them. And so what typically happens is metals are all the way to the left side of the table. They have low valence electron numbers, and this leads to them having low ionization energy and low electronegativity. Typically, a metal like sodium wants to lose its electron, and it's good at losing its electron. It doesn't take a lot of energy. It doesn't try to attract new electrons, and therefore they typically become positive elements, or positive ions. Nonmetals have high ionization energy. Whoa, that came out wacky. Have high ionization energy and high electronegativity because they have, here's a color for you, because they have 7 or 6 valence electrons, they really want to gain electrons. So it takes a lot of energy for them to be lost, and they are very good at attracting new electrons. And so they typically become negative. Oh, silly goose. They typically become negative because they are busy gaining electrons. So, here are some of the trends that we're going to talk about on the next page, but I can talk about them right now. These are our metals. These are our nonmetals. And a lot of these can be, thought about. Metallic characteristic increases as we move down this way for the reasons we mentioned before. Non-metallic characteristics increase as we go up in this direction. We'll talk about the trends on the next page and why these look the way that they look. But this is a good reference for you, as well as your reference table. Your reference table is a great place for you to look to see what the trends are. A lot of the times, the Regents will ask a question about what is the trend of electronegativity across the period. And most people might remember that it does increase as you go across. But let's just say you don't. What you can do is go right to your reference table, and you can say, all right, if I start in period 2, lithium has an electronegativity of 1.0. And then it becomes 1.6 for beryllium. It becomes 2.0 for boron. It becomes 2.6 for carbon. 3.0 for nitrogen. 3.4 for oxygen. And 4.0 for fluorine. So the trend, which is given right here by your reference table, says that as I go across the period, the electronegativity increases. All right, so that's how, you can always go back and check on your trends. Ionization energy and electronegativity increase across the period. And as we were just talking, you can always check those trends. The reason why is a little different. Okay, like that's not something you can necessarily look on the reference table. So electronegativity and ionization energy increase across the period, but atomic radius gets smaller. The atoms shrink as you go across the table. This is because as you go across a period, the nuclear charge of the shell, of the electron shell, is increasing. It's a stronger nuclear attraction within the same shell of the nucleus. And so with a stronger pull, here's my example. Boom, there's a nucleus. It pulls on an electron like so. But if we increase that nucleus charge, that big, big positive, that negative is much more attracted and it shrinks the size of the atom. Ionization energy and electronegativity decrease across the period. So, did I write period? Oh, you silly goose. Decrease down a group. All right, forget I said that. Ionization energy and electronegativity decrease down a group. So as we go down, the periodic table, atoms become easier to remove electrons, right? Lower ionization energy, and it becomes more difficult for them to gain new ones. Low electronegativity. The atomic radius this time does the opposite, as it is increasing. This reason is much more easy for us to understand, and it just comes down to an increased number of electron shells. And therefore, the nucleus has less pull. Even though there are more protons, it has less pull because there are more shells it needs to pull on. Right? This picture shows it perfectly. Right? The radius is increasing as we go down because each time we go down, an additional electron shell is being added. And that increases the size of the radius. So I hope you really enjoyed this. I hope this helped you out quite a bit. Thank you for watching the review. Talk to you soon.